Hello everyone. Today we're going to talk about interference, diffraction, polarization, and color. So we're going to start with constructive and destructive interference, or CI and DI. So in this first example we have two waves, y1 is sine of x and y2 is sine of x. And this is an example of constructive interference, because when we add those two waves together, you get a wave of larger amplitude, 2 sine of x. In this next example, if we shift the wave by half of a wavelength, so sine of x minus pi, we have an example of DI here, right? Because if we add the two waves, the crest and the trough cancel, and so we get 0. And so in this last example, if we just shift it by an entire wavelength, sine of x minus 2 pi, we have another example of CI. And so we make the general observation that delta y is equal to n times lambda for CI, and delta y is n plus 1/2 times lambda for DI because of shifting. And so there's a quick principle that we have Huygens principle, which tells us that waves will expand radially outward in all directions. And so we're going to explore that using this demonstration. We have the ripple tank applet right here, and you can see that there's two wave sources here, and all the black areas are areas of DI, and in between we have the areas of CI. So you can take a look at that. And then we have, if we have this double slit experiment, which we'll talk about, we have a very similar idea of DI and CI, which is just expanding radially outward right here. You can see that. And we'll cover the single slit experiment in a bit less detail, but there's a very similar idea, but there's a more pronounced central maximum, like a bigger center right here. You can see that. So now let's discuss the double slit experiment performed by Thomas Young in 1801. And so here you can see those waves, and in the intersection points, you have points of a CI, and in between you have the points of DI. Whenever these waves will intersect, you have CI, and in between you have DI. And so this variable D right here is the distance between the two slits, and the variable L is the distance to the screen. So we have the variable delta y, which is our path length difference, which is the magnitude of y1 minus y2. And you see that the path length difference is 0 when both the path lengths are the same, right? The path length that light takes to reach to the screen. And so we can have like delta y equals lambda, which is CI. It's made from the points of CI. So you can see the blue lines are connecting all those points, which are points of constructive interference. And so we can have like delta y equals lambda. And if we have like lambda over 2 or negative lambda over 2, that's all DI in between those. And so you can see that we're going to focus on the point delta y equals lambda, which is the green triangle. You can see that. So we can make an example that, we can make an assumption that D is much less than L. And so this triangle that's marked in green over here, there's like a reddish green, actually looks a lot more like this. And so I dropped a perpendicular here, which makes these approximately isosceles due to our assumptions. And so we have the angle theta 1, which is approximately theta. It's the small one that I drew in here. And it's within 1%. And so through basic trigonometry, we can see that the sine of theta 1 right here is just delta y divided by d. So delta y is d sine theta, which is n times lambda from CI, the identity we covered above. And this also works for the single slit experiment, which has a more pronounced central maximum. So at the bottom here, we have a quick example problem. So just take a moment to read over this, pause the video, take a few seconds. And now I'm going to cover the solution. So it's asking for the difference in path length from the two slits at the center of the first bright fringe above the central maximum. So central maximum is delta y equals 0. And so the first bright fringe or area of CI is actually this right here. And so our answer is just delta y equals lambda. Very simple question. And there's like a few options. This one like 3/4 lambda and 3/2 lambda, for example. But the right answer is actually lambda, right? Because they only want the difference in path length. So this would be the right answer in this case. Next, we're going to cover a very important derivation. And we know this already. We know this from CI. And we have the identity that tangent of theta is S over L, where S is just the distance from the central maximum, which is the distance from this point right here. So for small theta, tangent of theta is approximately sine of theta. through the quotient identity right here, because cosine is like approximately 1. So we substitute this into here, and we get ds over L is equal to n times lambda. So S equals n times L times lambda divided by d. Here's another example problem. Please take a moment to read that, a few seconds right here, and then try to think about this and work through the problem. Now I'm going to cover the solution. So we use our identity that we just derived, and we're determining the wavelength, right? So we have lambda equals d times S divided by n times L. So we should know what all the variables mean and substitute in. So d is the distance between the slits, and that's just 3 times 10 to the minus 6th meter. We have S, which is the distance from the central maximum, which we covered earlier, right? That's 0.004 meter. Then we have N, which is just 1 because we're using the first bright maximum, first point of CI. And then we have L, which is just the distance to the screen, which is just 2 meters. And so if we substitute all that in, we get 6 nanometers, which is the final answer. Now we're going to discuss polarization. So light waves are electromagnetic waves, right? And so if you have a polarizer, that has a special chemical attached to it, which will make it polarized in a certain direction and will only let light pass through a certain direction, right? Because it filters the electric field, right? So this one is polarized in the I hat direction, you can see that. And so it's going to block out the J hat component completely, right? Because you can express the electric field like this. And so the energy carried by wave is proportional to the square of the amplitude. And so it's proportional to this, cosine squared of theta. And so we're going to explore that with another demonstration regarding the polarized paper. So here we have some polarized sheets. And so here you're able to see the light because the light is passing through the polarized sheet. But if I take this top one and I rotate it by 90 degrees, what's happening is now the light is getting blocked and it's actually getting reflected back onto the table. Right, so you saw those two states where light is passing through and where light is reflected. Now if we take this 45 degrees and we put it right in between, let me slip that in between, then we see that some of the light is actually passed through, right? Some of it is reflected on the table and some of it is still passing through. And so that's a very important idea, right? It's not that this other sheet is generating the light, but it's just by adding the sheet in, and we're going to explore how that's actually possible. So I wrote this out. So if we have, I changed the direction, it's vertically polarized here in the drawing, but don't mind that. And we see that if they're polarized in the same way, 0 degrees and 0 degrees, then 100% of photons will pass through. But if it's 0 degrees and 90 degrees, like when you were seeing like the light getting blocked, right? That means that 0% of photons pass through in the ideal case, right? And in this case, if we put like that 45-degree filter in between, we can use our cosine squared theta identity, right? And so we use 45 degrees, and that gives us 1/2, right? And so if light is passing through from this first one, this 0 degrees, to the 45 degrees, and that'll give you a 1/2. And then from 90 degrees, that's 45 degrees from 45 degrees, which gives you another 1/2. So 1/2 times 1/2 will make 1/4 photons. So if you send in like 100 photons through, then you would expect to get 25 photons. That's the expected value. So here's another concept in polarization via an example. So spend a minute or two and think about this problem. And so now I'm going to show the solution. The solution is actually A, right? It's when light is reflected that it gets polarized. And so you can see that it's because light is oscillating in the same direction when it is reflected. And so regarding answer choice E, there's no polarization with the same index of refraction. The polarization will not occur. So now we're going to talk about color. This, what you're seeing right here, this photo, is the result of the double-slit experiment done with sunlight. And you can see the rainbow pattern, right? Why is that the case? Because the reds are meeting with the reds and the blue are going to meet with the blues in CI. And that's because of the color, right? The visible light spectrum in the electromagnetic spectrum. So it's all because of these wavelengths, really. The wavelengths are doing this with the color, and your eyes are able to detect certain wavelengths, which are the colors, right? And so the energy is increasing from left to right in this case. So as the wavelength is decreasing, see the wavelength is decreasing from left to right, and the energy will increase from left to right, and the frequency is also going to increase from left to right. You can look at that because of the E equals h nu. And we also have the acronym Roy G Biv. And so energy and frequency is increasing from down here. So violet has the most energy and frequency. And then the wavelength is decreasing from the bottom to the top. And so this kind of explains like rainbows, right? Because light is getting polarized when it's reflecting from like the water droplets, right? And so it actually works very similarly to this double-slit experiment with polarization, combining those two ideas, right? And that kind of shows how the rainbow is getting formed from these different colors and from the reflection off of the water droplet. Alright, so those are all the main concepts that I wanted to cover. So thank you everyone for listening, and good luck on the SAT Physics exam.